Hello everyone, and welcome to the presentation of our paper titled GAP, Differentially Private Graph Neural Networks with Aggregation Perturbation. My name is Sina Sajjad Manesh, and I'm a PhD student at the DIAB Research Institute and EPFL. And this is a joint work with my colleagues, Ali Shahin Shamsawadi from the Turing Institute, Aurelien Belle from INRIA, and Daniel Gatica-Perez, also from EDIAB and EPFL. Graph neural networks, or GNNs, have emerged since the last couple of years as a state-of-the-art algorithms for learning on graph data. They are used in a variety of tasks, such as node classification and link prediction, and have numerous applications in fields like recommendation systems, credit issuing, traffic forecasting, and drug discovery, among others. As we increasingly use GNNs, one crucial aspect we need to consider is that graph data can often be privacy sensitive. For instance, it could include users' personal attributes, financial transactions, or even medical information. However, like other machine learning models, GNNs are also not immune to privacy attacks and can leak private information. For example, link stealing attack or membership inference attack can compromise the privacy of the individuals represented in the graph data. This brings us to a critical question. How can we preserve the privacy of individuals when learning over graph data? This question forms the core motivation behind our work and is what we aim to address with our proposed solution. To this end, we present GAP, which is a novel GNN that comes with differential privacy guarantees. Specifically, GAP uses aggregation perturbation, which is a unique approach to preserving the privacy of graph data. It also has a tailored architecture that allows us to maintain the privacy costs. This ensures that we can provide strong privacy guarantees while still enabling effective learning on the graph data. And finally, we provide a formal privacy analysis for both edge-level and node-level DP. Before we dive into the details of GAP, let's first take a moment to understand the basics of GNNs. In a GNN, each node is associated with a feature vector, and the goal is to learn a function that can generate embeddings for these nodes based on their features and the structure of the graph. These embeddings can then be used for various tasks, such as node classification or link prediction. Internally, a GNN is composed of multiple layers, where each layer basically takes input node representations along with the graph's topological information, like in the form of an adjacency matrix, and it generates a new embedding vector for each node. But inside each layer, each node aggregates the features of its neighbors and then updates its own embedding vector using a learnable transformation function like an MLP. But as I said earlier, these models can leak private information, so we use differential privacy to make them privacy saving. In general, the guarantee of a DP algorithm is that if you go from one dataset to another neighboring dataset by adding or removing any individual sample, the output distribution of the algorithm on the two datasets should not change much. Formally, we can say that a randomized algorithm is epsilon DP if for all neighboring datasets and all sets of outputs, the ratio of the probability of the algorithm outputting a value in that set on the two datasets is bounded by e to the epsilon. But when dealing with graph datasets, we need to define what we mean by neighboring graphs. In this context, sometimes we're concerned with protecting individual edges. This is what we call edge-level DP. So in this case, two neighboring graphs differ by at most one edge, which means that we can go from one to the other by adding or removing a single edge. But if we're concerned with protecting individual nodes, then we're dealing with node-level DP. So in this case, the two graphs differ by at most one node and all its adjacent edges. So now the goal is to train GNNs with differential privacy. But the question is why we can't just use the standard DP algorithm like DPSGD for training these models. The first issue is that in GNNs, the output embedding of a node not only depends on its own features, but also on the features of its neighbors and the neighbors of its neighbors, and so on, because of the aggregation mechanism. More specifically, with a K-layer GNN, each node affects the embedding of all the nodes in its K-hub neighborhood. So a small change in the input graph can result in a very large number of gradient terms changing at once, maybe even all of them, which is simply too much for gradient-based algorithms like DPSGD to handle. The second reason is that even if we somehow manage to train a private GNN model, the inference step can still leak private information. And this is mainly because the GNN uses the graph data again at the inference time. Specifically, To perform the inference for a node, the model needs to get back to the graph again and fetch data from its neighbors to compute the aggregations. And this step can leak private information and practically voids the privacy guarantees of your training algorithm. So as a result, with GNNs, it's not enough to just make the learning algorithm private. You need to also have a differentially private inference mechanism. So to tackle both of these challenges, we propose aggregation perturbation, which basically means that we add noise to the output of the aggregation steps of the GNN instead of its gradients. This can prevent the exploding sensitivity problem because we're not delaying the noise addition to the end, but we add noise immediately after every access to graph data to make them DP. And so the whole forward path of the model becomes a composition of smaller differentially private steps. And because the forward path becomes DP, the output of the model also becomes DP, so it ensures inference privacy as well. But using this aggregation perturbation approach with like standard GNN models would be very expensive in terms of privacy cost, because then we need to add noise at every forward pass and every layer of the GNN and at every training iteration. And this process consumes a lot of privacy budgets. So what we do to address this issue is that we decouple the aggregation operations from the model parameters, such that the aggregation steps become independent of the model parameters, and therefore can be pre-computed and perturbed once and for all to maintain privacy budget. So we come at our proposed GNN model, which we call it GNN with aggregation perturbation, or GAP for short. We have three modules in GAP: the encoder module, the aggregation module, and the classification module. The encoder module is only used for reducing the dimensionality of input features for the aggregation module. And it's simply an encoder MLP that is pre-trained before the training of the rest of the model, using only the node features and labels. Then we have the aggregation module that is just a series of normalization, aggregation, and perturbation steps that are computed once and then cached for training the classification module. And finally, the classification module is an MLP-only model that is trained using the pre-computed noisy aggregated features and node labels without further accessing the graph structure. So our GAP architecture comes with the following advantages. First, it can provide edge-level DP because every access to the adjacency matrix is immediately followed by adding noise. Second, it can provide node-level DP if we train the encoder and classification modules using DPSGD, but this only works for bounded degree graphs. Also, there is no limit on the number of aggregation steps, though there is a trade-off between the number of steps and the privacy cost. But in general, GAP can benefit from multiple aggregation steps, which is useful for capturing long-range dependencies in the graph. And finally, not only it provides inference privacy, but also it does not require any additional cost for inference privacy beyond the cost of training because of the caching mechanism. So basically, it provides zero cost inference privacy. Okay, so now let's see how GAP performs in practice. We evaluate GAP on 3 medium to large scale real-world graph data sets, namely Facebook, Reddit, and Amazon, which are different in terms of the number of nodes, number of edges, features, and density. We focus on the node classification task, but the goal is to predict the label of each node in the graph. And we compare GAP with two baselines, MLP and GraphSage. MLP is a simple MLP model that does not use the graph edges and thus has perfect edge-level privacy. We also make it node-level DP by training it using DPSGD. Another baseline is GraphSage, which is one of the most popular GNN models. We make it edge-level DP by adding noise directly to the adjacency matrix. And for node-level DP, we use an extension of the DPSGD algorithm to GNNs that is proposed in a previous work. First, we compare GAP and GraphSage in the non-private setting without adding any noise, just to see how much accuracy we lose only by changing the architecture. We can see from this table that GAP is very competitive with GraphSage and even outperforms it on Reddit datasets. So we can say that we do not lose much accuracy by using GAP instead of GraphSage. So now let's see how GAP performs in the edge-level DP setting. For this experiment, we change the value of epsilon from 0.1 to 8, and we report the accuracy of different methods on the test set. We can see that our GAP method, which is the blue curve, has much better accuracy privacy trade-offs compared to GraphSage and MLP. And it always performs better than the MLP model that does not use the graph edges. Here's also the same experiment in the node level DP setting. Here we choose higher epsilon values from 1 to 16 because the node level DP is harder to achieve as we need to hide much larger differences and thus requires higher epsilon values. Again, we can see that gap, the pink curve, still has much better accuracy privacy trade-offs compared to the other methods. In the node level DP experiment, we used pretty large epsilon values. So one question is that if these values will provide meaningful privacy. To answer this question, we also use the membership inference attack to empirically measure the privacy of our method. Here we use the same range of epsilon values as before, and we report the mean AUC of the membership inference attack. We can see that while the attack is pretty successful in the non-private setting, it performs close to the random guessing in the private setting, even when epsilon is as large as 16. So to conclude, having a differentially private GNN model is important because GNNs can leak private information. But achieving DP in GNNs is challenging because we have the exploding sensitivity issue, and also we need inference privacy. We proposed GAP, which is a differentially private GNN model based on the aggregation perturbation technique. It can achieve both H-level and no-level DP. It also supports multi-layer aggregations and provides inference privacy. Thank you very much for your attention. You can find the code for our GAP model on GitHub. And if you have any questions, please don't hesitate to get in touch.